Hello, this is Dr. James Yohe. You can't see me, but there I am. And this is for business statistics, and we're working on chapters 5 and 6. Mostly we're going to focus on the hypothesis testing, and I'm going to use the example from your homework, chapter 6, problem number 27, except I'm going to change the numbers a little bit, okay? But it'll be exactly the same. I'm really just going to change one number, and that's the sample mean, okay? And we're going to go over how to do hypothesis testing using the Z-stat. Okay, I don't have any sort of material that can really pop up on the screen here, except for some of the stuff from chapter 6, and the PowerPoint slides on 6 aren't particularly good, but we're going to go over it anyway. Okay. So briefly, and I'm going to go through this fast because I'm mostly just concentrating on how to do the problems. Okay, we're talking about a sampling distribution. Okay, so here we've taken some sample from sleep times based on a study provided by data from an MIT study, and times taken in minutes for 50 volunteers to fall asleep. So these are the periods of time it took them to fall asleep. Okay, that's the data. Now, a parameter is a numerical descriptive measure of a population. So that's kind of what we're interested in. We're taking this sample and we're going to use it to infer about a population as a whole. So all males, could take this medicine and how long it takes them to fall asleep. The parameter is a numerical descriptive measure of a population because it's based on the observations in the population. Its value is almost always unknown. Okay, it would be impossible to go out and give this medicine to every male and see how long it takes them to fall asleep, so we'd have to do a sample. When we do a sample, the numerical information we get from that sample is called a sample statistic, or just commonly referred to as a statistic. And that is a numerical descriptive measure of a sample. The mean, the median, the mode, these can also all be obtained as information about a sample, and we want to infer from that sample about the population as a whole. Okay, so we are going to use sample statistics to give us an idea of what the actual population parameter is, say the mean. It's one of the most common things we do. Okay, now population parameters listed next to the sample statistics. A mean, a population parameter for a mean, is mu. That's this population mean, mu. That's a Greek letter mu. We use the Greek letters for population parameters, and we use regular letters, English letters, or whatever you want to call them, for sample statistics. So the mean for a sample is x bar. We might use x bar, the sample mean, to infer about the population mean. The variance that we get from a sample is s squared. And we might use that to tell us something about the population parameter, sigma squared. That's a Greek sigma. The standard deviation, which we all know is the square root of the variance. For a sample statistic, we abbreviate that with an S. When we use as a population parameter, it is sigma. Okay. This sample variance and standard deviations, those are our best guesses as to what these population parameters actually are. And then when we do binomial proportions, we use p hat if it's from a sample, and we might infer about p. I guess it's the only one, I think it's a pi, but about the binomial proportion. Okay. Now, here we have a sample. X bar is closer to m than to mu. Okay. In another sample, m is closer to x bar than to mu. Okay. So here, the median, the sample population, and the sample mean and the population mean. Okay, you can see how those are set up. Now, a sampling distribution is a sample statistic calculated from a sample of n, in this case, temperature measurements, is the probability distribution of the statistic. So we're taking some sample of size n, little n. Okay, that's the number of items we sampled, say 12. Okay, and we're taking this from a big population. Okay, now if you think about it, think of all the different little collections of 12 we could pull out of, say, the United States. There's a huge number of them. Some of them could be very close to the actual, when we calculate the mean of them, some of them, the mean could be real close to the actual population mean, but some of them, if we got outliers, could be really far apart. So we could get a whole distribution of sampling means, in this case, from that population. So what we're going to try and do is say within some level of confidence, say 95%, does this sample mean fall within a 95% confidence level of that mean? And we will construct a confidence interval. And if that if that sample statistic falls within that range, we will say that it is possible that the hypothesized population parameter that we hypothesized about, say it's equal to 3, that this sample falls within a range that makes it reasonable that it could be 3. Say we get 4.5. Is 4.5 too far away from 3 for us to reasonably assume or expect that that population parameter could be 3, or is it close enough? And that depends on the variance of the sample and the population. Okay, and that's what we're trying to do here. Okay, so here we have a sampling distribution for X bar based on a sample of 25 temperature measurements. Okay, so we measured the temperature and we hypothesized that the population parameter is 10 degrees Celsius or whatever. That's the average temperature for South Dakota or something. Okay, we could get sample means from 0, negative, all the way up to an infinite number. Okay, depending upon which 25 days we picked out of the last 50 years. Okay, it's possible, even in a random sample, that we could have grabbed some outliers, right? We could have picked the coldest days in the year, the hottest days in the year randomly. But the probability of doing that is very small. On average, okay, those sample means are going to be clustered around the population parameter we're examining. So if it's 10 and it falls close here, we can't say, no, it's not 10 anymore. But if it falls way out here on the ends, the probability, and remember, probability goes on this axis, the probability of something getting something way out here on these tails, if the population parameter is 10, is remotely small. And we're going to pick this level of confidence, say 95%, and that'll give us a range, maybe between 8 and 12. So if we take the sample and it comes out between, say, 8 and 12, that's a pretty good indication that it could be 10. We can't throw 10 out. We can only fail to reject our null hypothesis that the average temperature is 10 degrees Celsius. We're not proving it, okay? We never accept a null hypothesis. We only reject or fail to reject it. If the sample mean fell way out here, the probability of that happening is so small that we reject the null hypothesis. We say, no, it's not 10. It could be some other number, or it could be greater than 10, okay? So we got all these different population means represented by this bell curve here. Sample means, I'm sorry, taken around a distribution with a population mean parameter of 10. We're picking some proportion, 95%, okay, and saying that it falls within a 95% probability. We're not going to reject the null, but it falls way out here on the tails, 2.5% each. We're going to reject the hypothesis that this population parameter is 10, okay? Now, two sampling distributions for estimating the population. Here we have a sampling distribution for statistic B and statistic A, okay? And you can see here that the variances for these two, okay, have different values in that sampling distribution, okay? Now, the way we look these things up, depending upon what type of problem we're doing, are based on the underlying distribution or assumptions about it. One of them is a uniform distribution. You can see here that if we take a sample of a certain size or a certain sample, the first 10 samples of n equals 11, thickness measurements from the uniform distribution, okay? Now here you can see we got different means, okay, from these 10 different sample size. These are the number of samples, I'm sorry. N is the size. And we got different means and different medians, all from the same population, okay? So we got the smallest we've got here, it looks like 169.46, and the largest is about 182.09. Now what we want to know here is that reasonable, that we could have some mean population that we hypothesized about before, but you can see we'll get different sampling means and medians from the same populations, okay? It's just the nature of sampling, okay? So here we have a histogram, right? You can see here X bar. These were the frequencies we got from some sampling distribution, but they're all sort of distributed around some number. That some number, the more samples we do, the closer this thing will collapse in on the true population parameter. The bigger the sample, the tighter the variance will be around that sample mean, okay? And oops, sorry, and there's the median there, okay? Now, properties. A point estimator of a population parameter is a rule or formula which tells us how to use the sample data to calculate a single number that can be used as an estimate of the population parameter. Knowing nothing else, our point estimate is always our best predictor, okay? Now, if we have an unbiased sample statistic for the parameter theta here, this could be a mean whatever, okay? Then the sampling distribution should be evenly distributed, in this case a normal distribution, about that parameter, okay? So these are different values, or the probability of getting a different value, say from 0 to 100, for that population parameter from a sample mean. We get all kinds of different sample means depending upon which items we picked out of the population, okay? And that is an unbiased estimator, okay? We get unbiased estimator of theta. A biased estimator would be some sample statistic we use to estimate this population parameter, but the mean of the sample means will be different from the population parameter. We want an unbiased estimator, not a biased one, okay? If the sampling distribution of a sample statistic has a mean equal to the population parameter, the statistic is intended to estimate, the statistic is said to be unbiased. Unbiased. If the mean of the sampling distribution is not equal to the parameter, the statistic is said to be biased. Okay, it could be here, right? Over or under. Okay. Now, when we have sampling distributions for two unbiased estimators, there's something else we want to look at. These are two unbiased estimators. The mean of the the mean of this sampling parameter, sampling statistic B here, its mean is the population parameter, but these sampling means have a much bigger variance to them. That makes them less efficient than A here. So we would want to use the sample statistic A to estimate this parameter rather than B, because it's more tightly compacted around the actual population parameter. It's more consistent. Okay. When you sample a uniform population, we have f of x, that is the probability of x. For a uniform population, when we sample it, the sample means all have the same probability of being selected. We can't get one less than 150. We can't get one more than 200. Okay? And we know the probability of anything between 150 and 200 is exactly equal to 1 over 50. Now, to calculate the probability of a sample mean, or anything out of a uniform probability, you take the high end of the uniform population, 200, subtract the low end. We can't get one less than 150. Okay? And whatever that leaves over, in this case 50, you put a 1 over it. And that is the probability of any value coming up as a sample mean between 150 and 200. You can't get more, you can't get less. Okay? It's a very simple probability distribution. Okay? Now, the properties of sampling distribution X. The mean of the population, the mean of the sampling distribution of X bar, those are your sample means, equals the mean of the sampled population. That is mu of X bar, the mean of the sampling distribution population. That's all the different samples we could ever grab out of a population. The mean of those sample distributions is expected value is mu. Okay? The standard deviation of the sampling distribution of X equals the standard deviation of the sampled population divided by the square root of the sample size. Okay? So the standard deviation of the sample means, that big old population of sample means we could take, is equal to the standard deviation of the population divided by the square root of x, of n. And n is the number of items in our sample. So the bigger the sample, the tighter this distribution of sampling means gets around the actual population parameter. So big samples would be better than small samples if we could take a big sample. Okay? Usually our sample size is determined by time and money considerations. Okay? And how certain we want to be about getting that hypothesis about the correct hypothesized sample parameter met. Now, there's an asterisk here, okay? The standard deviation of the of the sample means is often referred to as the standard error of the mean. And that's to differentiate it from the standard deviation of the sample, which we'll look at later. Those are two different things. So the standard error of the mean, all right? In a random sample of if a random sample of n observation is selected from a population with a normal distribution, the sampling distribution of the sample means will be a normal distribution. And that's important. If we know that something is normally distributed, and we take a bunch of different samples from that population of sample means will be normally distributed just like the population. Okay, and that is theorem 6.1. Theorem 6.2 is something called the central limit theorem. Consider a random sample of n observations selected from a population with a mean of mu and a standard deviation of sigma. Okay? Then, when n is sufficiently large, the sampling distribution of the sample means x bar will be approximately a normal distribution with mean I'm sorry about that. Now here, consider a random sample of n observations selected from a population, any population, with a mean of mu and a standard deviation of sigma. If we enlarge our sample enough, then the sampling of the means, okay, the distribution of the sample means will become a normal distribution with a mean equal to mu and a standard deviation equal to the standard deviation of the population over the square root of n. The larger the sample, the better will be the normal approximation to that sample. Again, apologize, okay? So the larger the sample size, the better that approximation will be. In the limit, as we increase n out to infinity, that whole distribution of sampling means as n gets bigger, gets closer and closer, and eventually, if we make it big enough, it will become distributed right up and down that population mean. Okay? Proof of this is beyond the book, but there is a proof. Okay? Now, you can see here, we have an original population. There's a square, there's an M, right? These three here are all not normal. As we increase n from 2 to 5, and then finally up to 30, all these sampling distributions start around 30 to approximate a normal distribution. And that's important when we decide whether or not to use a Z statistic or a T for our hypothesis testing. 30 is usually the limit, okay? And you can see here. And then this is for a normal bell-shaped, and you can see if you have a normal bell-shaped curve, the sampling means are always normally distributed. They always have that bell-shaped curve. And as n gets bigger, all of these start to collapse in on the population parameter if we have an unbiased estimator. Okay? You can see here, this is squiggly line. We don't have a name for that one, okay? But as n gets big enough, the sampling means will start to take on a normal shape, okay, when we take samples from it. Okay. Now here, this is what we're going to be doing. This is an example of a one-tailed test, maybe. So here, we believe, or that mu is, in this case, 80. Okay. Now, we have a sampling mean distribution, and it has a bell-shaped curve here. And we want to know at what point, if we get a sampling mean as we go to the right here in this case, at what point does that sampling mean go from being go from not disproving that the sample mean is 80 to this blue region here, where we say if the sample mean comes outside of there, maybe it's too extreme for us to reasonably accept 80 as the population parameter. These are sample means of a certain size. Okay? And in this case, 1 is the standard deviation of the sample mean. So we've got 1, 2 standard deviations to the right of the mean. And anything past that, we're going to say, no, that's too extreme. Because remember, about 95% of all sample means will fall within plus or minus 2 standard deviations, in this case from the empirical rule. We're going to use something called a Z statistic for a normal distribution and a T where we don't know the distribution later on. But let's just stick with this for now. Okay, here's another example of a one-tailed test. We hypothesize that this thing is 54. We've got a sample size of 50. We calculate out a certain distance, in this case to 52, it looks like, although it looks like less than 52, but it says 52. And if our sample mean is less than or equal to 52 here, we're going to reject this null hypothesis that the population parameter is 54. If we get, say, a sample mean of 50, we're going to say, no, it's probably unlikely that it could be 54, and we're going to reject that null hypothesis. Okay? Now, get here. Now, this part of the problem is the PowerPoints don't include anything past that, unfortunately. So we're going to do the rest of this by hand. Okay? And we're going to use problem 627 of your textbook, and that is on page 309, and I apologize for the bad camera work. Okay, here, teacher perception of child behavior. Now, if you get your book out, pause this, get your book out. Okay, the developmental psychology journal published a study on teacher perceptions of the behavior of elementary school students. Okay, and they rated these students on aggressive behavior. They had a sample size of 11,160 students. So they sampled this 11,160 students from New York City public school children, and their teachers evaluated them. This child threatens or bullies others in order to get his own way. Responses were measured on a scale from 1 of being never to 5 always. Summary statistics for the sample of this 11,160 students were reported as X bar, the sample mean, came back as 2.15. The standard deviation of the sample came out to be 1.05. Now, we're going to hypothesize, and this is going to be our null hypothesis, that mu is equal to 3.0. Where would we get that number? We might get that number from other experiments, other evidence. We might get that number a priori. We might say, well, we would expect half of the kids to be really bad, get 4s and 5s, and some of the kids to be fairly good and get 2s and 1s and maybe 2s and maybe some 1s, and say on average it'd be 3. Your knowledge about the subject would give you the idea of what this hypothesized parameter would be. Now, this is sort of a silly example from the textbook. One of the things might be if we were having, say we had a machine, and instead of rating the students how good or bad they are or big bullies they are. Instead, maybe we're counting the number of defects that come off of a tire making machine every day. And we might say, well, the manufacturer says that we can expect 3 defects per day from the machine. Okay, then we might go and collect data off of these machines as we run them and count the number of defects and calculate a sample mean, and then say, hey, does this sample mean we got, is it reasonable we could get this kind of a sample mean from a population where the mean was 3? And that's what we're testing here, except it's with bully children. It makes a little bit more sense when we talk about defects off of a machine where we might get that 3.0 number. Okay, but we're talking about bullied children. Our null hypothesis would be that mu does not equal 3.4. Now, if you have an equality that is a two-tailed test, and that's important to remember. If you have a greater than and equal to, less than or equal to in your null hypothesis, that is going to be a one-tailed test. Okay? And that's what we're testing. Here, we're testing, is the population parameter, is it reasonable to think that it could still be 3, even though we got a sample that didn't come up right at 3? Or is it not reasonable, that number's so far away from 3 that we cannot assume that it's 3? It's not reasonable to think it could still be 3. It's something else possibly. Okay? And we would reject that null and accept the alternative. You always have an equality in the null. It's either an equal, less than and equal to, or greater than or equal to. That's always in your null. And we abbreviate that H sub 0. Your alternative is just the opposite of what you have up here. So I have an equality up here. My null is going to be an inequality. If I have a less than or greater, less than or equal to here, my null is going to be greater than. Not equal, just greater than. If I have a greater than or equal to, my null is going to have a less than down here. Okay? All the sample space has to be covered by your null and your alternative hypothesis. That just simply means we can't get a value that isn't contained here or here. That's all it means. That's step 1. Okay, actually step 2. Step 1 is read the problem. Okay, read the problem, understand it thoroughly, write all of your data out up here so you don't have to keep looking through the problem for it, and then write your null and your alternative. It will be described to you in the problem. So here we've got the summary statistics listed, we've got our null hypothesis and our alternative. In words of the problem, define a type 1 error and a type 2 error. There is a beautiful little table in the book right here that explains this. And it's hard for me to get it close enough. Okay? Now here we have the conclusion from our experiment. Accept H naught, which we never do. We just fail to reject it, okay? We never accept a true null hypothesis. Or we reject H naught, and that's our alternative hypothesis, okay? Now, just because we fail to reject or reject the null, that doesn't mean we're correct. No matter what we do, there is a probability that we could accept the null hypothesis and it's true. Okay? That's what we want. Okay? We accept the null as being true when it is. That's the correct decision. We made the right choice. There is a probability, however, of a type 1 error. We could we could reject the null hypothesis when it was in fact true. See here, reject the null when it is in fact true. That's a type 1 error. That level of type 1 error is determined by what we call your alpha, okay? And the alpha is selected by the researcher. What probability are we willing to go to when we reject this? What type of probability are we willing to accept as reasonable of getting this type 1 error? And that's your alpha. The alpha is the probability that you commit a type 1 error and you pick it. The smaller the alpha, the bigger your confidence interval is going to be, okay? And the less precise your estimate has to be to accept the null, and that leaves you open to a type 1 error. A type 2 error is the probability of accepting a null hypothesis when it is false. This is HA, the alternative is true. If you accept the null hypothesis and the alternative is true, you've committed a type 2 error. And the probability of committing a type 2 error is known as a beta error. Okay, and that's a type 2 error. The probability of committing a type 2 is known as a beta. If you rejected the null and the alternative was true, you accepted the alternative hypothesis, then that's the correct decision. So here, no error, no error. If we accept the null and it's false, that's a type 1 error. If we reject the null and it's true, that's a type 1 error. We reject the null in our experiment, but it was true. That's a type 1 error. We pick the probability of that happening. If, on the other hand, we accept the null when the alternative is true, that's a type 2 error. Okay? Now, when conducting a test of hypothesis, because the measure of reliability, B, is equal to the probability of a type 2 error, is almost always unknown. If the test statistic does not fall in the rejection region, it is better to state the conclusion as insufficient evidence to reject H naught. Okay? So remember that. All right? Then we need the steps to testing a null hypothesis. And I wish I had this on a slide, but instead I'm going to write them here. Okay, I told you step 1 is read the problem thoroughly. They leave that out. So they say step 1 is to construct your null hypothesis. We did that here. Step 2, I'm going to use their numbers. Just remember to read your problems. Step 2 is to construct your alternative hypothesis, and I told you how to do that earlier. It's the opposite sign of what you put in your null. Okay? Step 3 is to choose a test statistic. Okay? And there are rules on that. Okay? A sample statistic used to decide whether to reject the null hypothesis. Now, if your sample size is greater than 30, you will use a Z. Or if we know the population standard deviation, okay, we can use that Z. If N is less than 30, that's greater than or equal to 30, I'm sorry, up there for the Z. If it's less than 30 and we don't know the standard deviation of the population, okay, so both these have to be true, just one of these has to be true, then we're going to use a T statistic. Okay? We're going to do a problem using the Z. So that's step 3. Our sample size is 11,160. So we're going to go step 3 with the Z. Step 4 is construct our rejection region. Okay. The numerical values of the test statistic for which the null hypothesis will be rejected. The rejection region is chosen so that the probability that A, the alpha, will contain the test statistic when the null hypothesis is true, okay, thereby leading to a type 1 error. So we're trying to assess the risk or the probability that we're willing to accept that this null hypothesis is true, but we reject it anyway. Okay? The standard numbers for this are 0.01%, 0.05, or 0.1. Okay? And this is referred to as a level of significance. The alpha is referred to as the level of significance. I wish I had a slide to do this for you on. Okay? So, how do we do that? I'm going to select an alpha, and I think the problem tells you. Most of the problems will tell you what the alpha is for the problem. And here, they tell us they want an alpha of 0.05. So 0.05 is our rejection region. Anything that falls in the outer 5% of a means distribution centered on 3 will say that rejects the null. It's not 3. It's less than or greater than 3, but it's not 3, equal to 3. Okay, and that is step 4. Step 5, assumptions. Clear statement of any assumptions made about the populations being sampled. Okay, that would be given to you in a problem, or you would know or believe this beforehand. For example, we might assume that the behavior of this children is distributed in a normal distribution, okay, a bell-shaped curve, or it might be a uniform distribution or some other distribution. Okay, that determines how we can calculate sample statistics. Okay, step 6. So our assumption here, step 5, normal distribution. Step 6, experiment and calculation of the test statistics. Performance of the sampling experiment and determination of the numerical values of the test statistic. We've already done that here. They said X bar, so this is step 6. X bar is equal to 2.15. We have an alpha of 0.05. So what we're going to do is we're going to go to the back of the book and find our Z tables, because we're using the Z. The Z table we're going to use is on page 555. It is table 3, areas under the normal curve. Now here, what we do is the normal curve always has a mean of 0 and a standard deviation of 1, and that'll come into importance later when I show you the equation on how to calculate it. We can turn all natural distributions, all bell curves, into this normal and use this Z statistic for our test. Now, we said, and we have to draw this picture, we said that we believe pretend I could draw a nice smooth bell curve here. I'm going to redraw it. Okay. I'm not feeling well today. My hand's shaking. Let's say here's that mu. Okay. Here's the value of the sample mean. We say it's 3. I'm going to put that here, 3.00. Now we can convert that into a z, and z will be 0 at the mean. Okay? Now, we said we want a 5% probability that we commit a type 1 error. Our alpha is 0.05 or 5%. We're doing a two-tailed test, so we have to divide that by 5, and we're going to get 0.025 out here on the tails. 0.025 is the probability of getting that. 0.025 is the probability of getting a value to the right of that where we reject this null hypothesis. So 0.025, 0.025 under that area of the curve. The rest of this is 95% of the sampling means. So if our sample mean falls within this white region here, we're going to fail to reject the null, or the book says accept it. If it falls outside, I'm going to color these in now. We know that those sample means are too far out. They're too far away from 3 for it to be 3, and we're going to reject that null hypothesis. Now, we don't know what those numbers are. To get those numbers, we need to calculate a Z statistic, okay, which we'll do in a minute. That's going to give us a low end and a high end here, okay? This will be negative Z number. That'll be a positive Z number, okay? Now, to find this, we need to remember that to the right of the mean for a normal distribution, 50% of all sample means will fall to the right and 50% will fall to the left, in this case of 3.0. So we need to know what percentage fall between the mean and the end of our acceptance region. Okay? To calculate that, you take 0.5, which is 50% to the right. You subtract out this rejection region. Its probability is 0.025. And we're going to get 0.4975. Okay? 0.4975 fall to the right and to the left of the mean, and we're still going to accept the mean. That number we're going to look up on the Z tables. I'm looking for 0.4975. 4975, and I've got it right there. 2.81. So the Z number at the high end of this range is 2.81. When we calculate our Z statistic, if it's greater than 2.81, we're going to reject the null hypothesis. If, on the other hand, we need a number over here at the low end, well, these are symmetrical. So if positive 2.81 Z statistic incorporates 0.4975 of the distribution to the right, negative 2.81 Z statistic falls to the left, and it incorporates 0.4975. So if we get a Z statistic less than 2.81, we're going to reject the null, or if it's greater than. Okay? Now, we can do it this way and calculate the Z statistic, or we could create a confidence interval. We'll do it both ways. Okay? The first thing I'm going to do is calculate a confidence interval. Okay? My confidence interval is equal to, CI, is equal to my hypothesized population mean or parameter plus or minus Z times the standard deviation. We don't know this, so we're going to use the sample. So my hypothesized mean was 3.0. I'm going to go plus or minus my Z, which was 2.81, times my sample standard deviation, which was, I believe it was 1.02. I want to make sure that's right before I say anything. Okay. 1.05. I was looking at it upside down. That's the standard deviation. So I got 1.05. So when I calculate this all out, I'm going to get 3.0 plus or minus, and I need my calculator for that because I can't do it off the top of my head. Is that my calculator now? There's my calculator. Okay. So I've got 2.81 times my standard deviation of 1.05. That comes out to be 2.9505. So I've got 3 plus or minus 2.95. We'll just leave it there. We'll round to there. So that means on the low end of my confidence interval, I'm going to subtract 2.95 from 3. The low end is going to be 0.05. So if my calculated mean is 0.5, is that right? Yeah, 0.05, I'm sorry, or lower, that's X bar, right? Then I'm going to reject the null. Then I'm going to add 2.95 here on the high end, 5.95. So if the calculated, or excuse me, if my sample mean comes out to be greater than 5.95, I'm going to reject my null hypothesis. Can everybody see that? Okay, that's one way of doing this, or we could just calculate a Z value and see if it falls in this range. Now, our sample mean was 2.15, right? To calculate a Z, the Z is equal to X bar minus mu over square root of the standard deviation. Where's my thing? Okay, to save us some time, and because I'm on cold medicine, I wrote the formula down wrong, I changed it. Z is equal to X bar minus mu, that's our sample mean, minus the population mean, or hypothesized population mean, divided by the standard deviation, in this case of the sample, that should be an S, divided by the square root of the number of observations in the sample. Okay. The sample mean was 2.15. We subtract 3 from that. We're going to divide that by the standard deviation of the sample over the square root of the 11,160 students we sampled. Okay. Bringing that down, okay, 2.15 minus 3 is negative 0.85. You got to keep the negative sign. 1.05 is the sample standard, the sample mean, the standard deviation of the sample mean, of the sample, I'm sorry, the sample, and the square root of 11,160 is 105.64. When we do the math here, my test statistic came out to be negative 85.59. That is my calculated Z. Comparing that to my test statistic, okay, which we got as being 5.595 on the high end, 0.05 on the low end, that is clearly lower than 0.05. If we go back to our drawing here, that number is way out here. It's in the negatives, negative 85. It's probably way over here off the page. That Z statistic is so far from zero that we have decided to reject the null hypothesis. We're going to reject the null hypothesis that the sample mean is equal to 3. It is not reasonable, given our sample, that the population mean could be 3. Okay, thank you very much for your time. I do apologize. I'm under cold medicine and I'm not on my game today, but this is the best I can do. Have a great day. Thank you. Goodbye.